Okay, can you see the screen online?
Yes, sir.
एक मिनिट हं. आज ऑफिस बंद असतं.
परीक्षेसाठी आम्ही एंट्रन्ससाठी
ते तुम्ही
भरला होता ऑनलाईन.
ते साठे कॉलेजला माझ्या मते व्हेन्यू इकडे नाहीये. तुम्हाला माहिती साठे कॉलेज माहितीये का?
इथं आम्हाला
संजीवन हॉस्पिटल नाही, हा तर इन्स्टिट्यूटचा ऍड्रेस झाला. पण तुम्हाला
फॉर्म भरलाय मागे नाहीये.
अच्छा, पण ती परीक्षा मला माहितीये तिकडे 10 वाजता होणार आहे ना सुरू. हा,
बरं.
तर मी तुम्हाला पत्ता पाठवू का? सांगाल
हो,
का? हा. कसं मोबाईलवर देऊ? तुम्हाला संजीवनी हॉस्पिटल माहितीये का कोणाला?
पुढे जावं लागेल.
नाही, या दिशेने.
त्या दिशेने.
हा, मी तुमचा मोबाईल द्या. हा, रिक्षाला कळेल. संजीवनी हॉस्पिटल एकदम फेमस आहे. त्याच्या बाजूला साठे कॉलेज.
साठे कॉलेज.
संजीवनी हॉस्पिटल.
हा, आणि साठे कॉलेज
लांब आहे का?
नाही, 1.5-2 किलोमीटर असेल. हा. रिक्षाने ह्या दिशेने रिक्षाने 5 मिनिटात पोचाल तुम्ही.
सरळ जायचं.
हो हो.
धन्यवाद.
Okay. I the code green in color. Okay. So I think last time some of you were not there, but just to quickly recap what I was trying to do. So I started with some geometric transformations and some basic ideas related to rotation, translation that we discussed. But what I want to start with today is like we'll revisit that topic, but this time we are going to do it in a 3 parallel threads. So what we saw last time was just one interpretation that we talked about what is displacement. Like if I give you a vector, you can apply that vector to an object and that will go from one place to another. But I know geometric transformation has this multi-dimensional approach. Like you can look at it like a geometry topic, you can look at it like an algebraic topic, you can look at it like a group theory topic. So there are 3-4 aspects to the same topic, and each of them has its own merits, and how you apply them is valuable. So just want to revisit that in that light. For that, one big thing I want to check. So how many of you are comfortable with complex numbers? Have you known the basic properties? Okay, you have no idea complex numbers. Online, can you raise your hand? Those who have some idea about complex numbers. Okay, so some of you have. So I will just quickly give a brief idea of complex numbers. I will not go into full details so that everybody can keep up with this. But I mean the thing is that geometric transformation have a very natural implication in terms of addition and multiplication with complex numbers. Okay, so that is why this is a very useful thing to know. So I mean the very basic thing about complex numbers is that it is just an extension of the real number set. That we take the set of all real numbers, but we know that there are some equations like x square plus 1 is equal to 0, which do not have a solution if x is real. And so to solve this problem, we created, let us say that this equation has a solution, and let us call that special solution I. Okay, we just invent that symbol that let I represent the solution of this equation. And then based on that, we start to develop properties that what properties that can this variable I have. And that is what leads to a whole set of, properties. Like for example, we discover that we can write expressions like A into I plus B, where I is this special symbol and A and B are real numbers. And so if I consider the set of all such symbols, that is what I start to call the complex number. Okay. So this is the theory. So those who already know, this is how you may probably know about this. And then you can figure out ways to define addition. Like for example, if I take two numbers of this type, like A1 plus IB1 and A2 times I plus B2, and then there are rules to add them. Like basically, like just the normal arithmetic that we do, I can take I common and A1 plus A2, B1 plus B2. Multiplication is similar, except that in multiplication, what happens? So when I multiply two numbers like A1I plus B1 times A2I plus B2, when you multiply it out, what happens is when you multiply, the bracket will be A1, A2 times I square. But we know that I is the solution of this equation. So basically what it is, this I square has to be minus. So whenever I see I square, I can replace it with -1. Okay. And so in that way, to expand this bracket, you get the equation that B1, B2 minus A1, A2. And okay, generally speaking, we write A plus BI instead of AI plus B, but doesn't matter. Like it is going to be the same thing. Plus I times A1, B2 plus A2, B1. Okay, so this is how we define addition and multiplication on this set of complex numbers, and all the other rules follow from this. So again, as I said, I don't want to spend my entire lecture on this, but if you are interested to learn more, and this is a very useful topic, complex numbers. Just one small comment I will make here, which is very interesting, is that this order of discussion is very important. That we don't just say that let I be square root of -1, which is often what you see in textbook. The specific decision is that this is the equation for which we could not find a solution. And so we called that symbol as I. But anybody can have this valid question. What is so special about this equation? Don't we have so many equations which don't have solutions in real numbers? Like, can you suggest some other solution, other equation which does not have a solution in real numbers? There are so many, right? What is so special about this equation? How about the equation? Very simple. X square plus 2 is equal to 0. Does this have a solution in real numbers? Okay. Then somebody may say, I want to call this the equation of the solution of this as my I. I don't agree with the standard theory. So I will come up my own. To avoid confusion, let us call it I2. Okay. So this is my new object called I2. And I develop my whole theory using I2. So now all my equations look like A times I2 plus B. And you'll see that will have its own definition of addition, multiplication, and the rules will be slightly different, right? Now, if you see what happened with multiplication, I square will be replaced by not -1, but -2. So some rules will change, but still you will get a valid arithmetic or algebra that all the addition, subtraction, multiplication, division, all these things get satisfied. And what we get is what we call the field. Okay, so what the basic properties like associativity, commutativity, distribution of addition, multiplication, all those get satisfied, we call it a field. So now the real question is, have we really created something different, or it is just a different name to the same object? I mean, for example, we do mathematics in English, but we couldn't do it in Marathi, no? I say 1 plus 2 is 3. Somebody will say 1 अधिक 2 is equal to 3. But just by changing the name, is it a different mathematical object? It is just a relabeling, right? So what if this new equation and the resulting field is just a relabeling of the original field? So this complex number set C1 and this complex number set C2, the question is, are they really the same or are they different? Okay, so this is a question for you to think about. I will not answer this question, but that if you think about this question, it will reveal a much more interesting layer of algebra and arithmetic, that there is a much deeper connection in all of this. And what I want to emphasize is that this goes beyond x square plus 2. Why not x square plus, what is today's year, 2023 is equal to 0. So complex number set 2023. Okay. This is going to define a different set of complex numbers. So are they really all these infinite set of complex numbers, or are they really different names given to the same complex number set? Okay, so this is so for those who already know complex numbers, or I want to point out that you think you know complex numbers, but if you have not answered all these questions, then your study is incomplete. Okay, so think about this question, that choose your favorite equation which does not have a solution. Call that solution some special name. You give it your own name. Okay, and then develop that theory, and then finally try to answer the question: Is that really a new? Uh, is it really new, or is it just a relabeling of the existing? And today we are going to see examples that what do I mean by this? That is it new or is it a relabeling of the existing? This is a very vague statement, but I will try to formalize it in some way today. That how geometric transformation gives us so many different ways of relabeling what appears to be the same thing. Okay, but anyway, I mean, I will not use complex numbers too much, but wherever I see the connection, I will definitely point it out because all of these are very important. Okay, so this is one of the tools which I will require. Then of course, geometric transformations. There are many construction kind of problems involved also in transformation. So there are some basic things that we may already know, like how to add to numbers, how to multiply two numbers using ruler and compass, square root, all those things are required. Okay. So then with this introduction out of the way, let me just revisit the topic of last time. So we are talking about transformations. Okay. And we said that transformation in general are some operations which go from the plane, that is r square, to itself, right? So a function that goes from the r square to itself. So r square is the short form used to denote the plane, because of course in two-dimensional coordinate system, every point can be written as a pair of real numbers. But what we said was that any function which goes from the plane to itself is not necessarily interesting. Like you could have the trivial function which maps all the points to just like the most boring function. No, it collapses the entire plane down to a single point. This is a function, but it's not an interesting function. So we typically don't call it a transformation. For the most part, the transformation we are talking about are bijections of some sort. Okay. So, so generally speaking, we are only going to deal with bijections. So bijection means that the function is 1, 1 and on 2, right? So in other words, if there are 2 points, like if I call this point 1 and point 2, it will never be the case that you apply the transformation and both point 1 and point 2 land in the same final position. That won't happen. Okay, because if that happens, then the difficulty is I cannot define an inverse transform. Because if this is the forward operation, in the reverse case, where will Q go? Will it go here or here? So to avoid that possibility, we are always going to deal with bijections. Okay? And then within that, we started to say that we have categories of transformations. So the first category is what we call a congruence transform. So congruence transform refers to those set of transform under which an object remains congruent to itself, which means that if you start with any object in the plane and you apply this transformation, you will get a different object, but which is congruent to the original one. Okay. And so within that, the first type that we talk is translation. Okay. Translation by a vector. Okay. So again, just to recap, what I mean by this is that you choose a vector. A vector is nothing but a kind of a line segment, but which has a direction. Like, so you start from A and you reach B. So those of you who are already studying vectors in physics, you can relate to this, right? In physics, you have the idea of displacement vector and those kind of things. So applying this transformation to any object like this one, we are going to take every point of my object and apply this transformation to it. So every vertex gets displayed this way. And so the original triangle lands in a new location, right? So that is what we call a translation. So I think it's easy to see that translation is a congruence transformation, right? Because the entire object is like picked up and placed in a different location. So that is what a translation is. Okay. So the important thing when we talk about any transformation is what are the inputs required to define the transformation. So here the important thing is that I cannot just say by translation this object goes there. I have to say by which vector. So that is like the input they have to give to define that object completely. Okay. And last time we saw some examples of how to use the translation, but we have not uploaded the recording yet, but I will do that today. Okay, so you will, those who missed it, you can see that. Okay, so that was translation. The second operation which I want to introduce today is called rotation. Okay. So rotation requires a point and one angle. Okay. So I have to define what is the center of my rotation and how much angle I have to apply. What is the how many degrees of rotation I want to do. Okay. So for example, if I have an object over here, some object doesn't have to be a regular shape also. Any random object of any shape can be taken. And if I choose this point as my center of rotation O and some angle theta. Okay. So what I'm going to do is that every point in my plane in that object, I'm going to rotate through the angle theta. Okay. To a new position. So the whole object will get rotated that way, right? So this whole object will maybe some shape like this will be not exactly accurate, but yeah. So like just imagine in your mind, literally that is a physical object which you pick up and rotate, you know. And if you do it to every point in that set, and the diagram doesn't show it, but clearly this is also congruence transformation, that the size and shape of the object will not change under rotation, right? So this is rotation. Okay. So now that we have two transformations here, we can do translation and we can do rotation. One question that we may want to ask is what happens if I combine them in various order? Like, for example, just take translation. If I translate one object through 3, 4 different vectors, like I first apply the vector AB, then I apply some vector CD, maybe some other vector EF. I do this operation one after the other. What will be the result of the combined effect of applying these three translations together? What will that be? Yes, correct. So basically, you can combine all these three vectors into one single vector, and that will directly give you the final result, right? So I mean, if you just put these vectors so that the tip of one vector is the start of the other one, right? So if I just copy this vector CD over here like this, okay, so this is a copy of CD. Let me call it C dash D dash, and similarly, I create a copy of EF, okay, E dash F dash. So basically, the point A goes to B, then from here to here and here to here. So I can say that equivalently, I can directly jump from here to here. So you see, I can add these three vectors and I'll get one more vector over here. And so effectively, what I'm saying is that not only the sum of these vectors is another vector, but the sum of three translations is one more translation. Okay. So, but typically we don't use the word sum there. We use what is called composition. So what I'm suggesting is that we can compose transforms. Okay. Okay. And so, I mean, just to how we can denote this in a very nice way. So let us start to use this notation. This is like a very formal way of, because every time writing the sentence translation by vector so and so is a very complicated process. So instead of that, let us start to use the shorthand notation. So when I say translation and in the bracket, I have to specify which is the vector. So if I say translation AB, this is the operation of applying the vector AB. Okay. So what is this object? This is itself a function. Okay. Because this function can take an input and it will generate an output. So if there is a point P over here, and to this point P, if I apply this let's say my vector AB looks like this. Okay. So, and suppose point P and uh, point P and point uh, Q are located like this. So this is, yeah, equal and parallel, roughly speaking. So then I can say that translation AB as a function, if I apply to the point P, I'll get point Q. So understand that, I mean, we are not typically used to having a phrase as a name of a function, but that is a new thing we are adding. And I think actually various authors have various notations. I don't know if there is any standard notation. Some people will just write the short form like trans. Some will write that AB as a suffix. So there are varieties of ways in which you can denote it, but it doesn't matter. As long as all of us agree on some one way, that is fine. Okay. So under what is the use of this operation, this like notation? Because now we can succinctly represent what we said earlier, that we can compose translation. So for example, do you see that I can write that suppose there is another vector BC over here. Okay. And so I apply the vector BC on this object now. So what I'll have to write, that translation of, so now the operation is translation to the vector BC applied to Q gives me R, for example. Okay. And now what will be the relation of P and R directly without involving Q? What will that operation look like? What is the vector to go from P to R directly? It is vector AC, right? So I could write, for example, translation vector AC applied to P goes to R. Okay. And the important thing is that the combined effect of these two is this one. And so if I want to write that in the one line, I could write, so translation of AB, no, sorry. Let me write it this way. Translation with vector AB, if I apply it to point P, so this is my object Q, and to this I'm directly going to apply translation of BC. So instead of writing it in two lines, I've written it in one line. That so this bracket is the operation of applying translation of point P. So basically the answer of this bracket is Q, right? So this bracket, the answer is Q, and so translation of BC on that Q will give me R. But what I can write on RHS is that this is the same as translation of AC the point. Okay. And so maybe you are already familiar with this idea that you can compose functions, that on the left hand side what is happening, I'm applying one function, and to the output of that I'm applying one more function again. So applying multiple functions in chain that way can be written as a composition. So I can write this as translation DC. And the composition operation is a small circle. You may have seen this somewhere. So this small circle represents chaining of two functions together. Like for example, if you have function f of g of x, I can write it as f composite g of x. So this f composite g is a new function which represents the operation of applying g then f. Or it always goes from right to left. Okay. Actually, again, some authors have different ideas. Some people still use left to right, but we will always stick from right to left because that is the order in which you put the brackets, right? And you can do this for multiple functions. Like there could be another function h, then you can do h composite f composite g. So this is a function where you apply g, then f, then h. So you can combine function this way. So if I use this notation to my advantage, so I can write LHS as translation of BC, a composite with translation of AB. This whole function applied to P is the same as translation of AC to P. And the important thing is this is true for every point P in the plane. There's nothing special about the point P. So what we have here is the left hand side is some function applied to point P is equal to the right hand side, which is also one function applied to the point P. So if you have, is it a different function or it is just the same function with a different name, right? Because at every input, the output is matching, right? Any point P you choose, the LHS and RHS are going to give you the same output. So effectively what we are saying is not just that, this composition is giving the same output, but this is the same function. So an even more compact way of writing is that we don't even have to write P. I'm saying that this function itself. So in other words, the translation operation of BC composite with translation of AB. This composition itself is this function. So this is a very powerful statement because just think about it. Now the point is nowhere in the picture. We are directly operating on functions themselves. I'm taking the operation of applying BC combined with the operation of AB, or in the reverse order is the same as applying this operation. So we are abstracting the point away, that the object on which we are doing the operation is no longer in the picture, and we don't require that. We can directly compose functions this way. Okay. And you can imagine that this can keep going, right? You can have 3, 4, 5, 6 translations. All of them at the end of it will be resulting in one translation. Okay. But as a result of this, something very interesting has happened. That now that we can combine translation, and for the time being, because I am tired of writing translation every time, so let me just call this capital T. Okay. So capital T represents translation. Okay. So just to write this in the shorter notation, translation BC and translation AB composite will give me translation AC. But now let me consider this set of all possible translation. Okay. So this is a T with a, it looks like a pi. Maybe not, maybe T with a 2. Right? Okay. It is a fancy new set. This is a set of all translations. In other words, you can choose any vector you want, and that vector will represent one translation, right? So we have put all such translations in this set. Okay. So for example, if you have 2 points A and B in the plane, right? So will I have like the vector AB, that translation will be in this set, right? So translation of vector AB will be in this set, right? Similarly, I can create a vector BA also, right? So translation of BA is also in this set. And so if I composite these two operations together, what am I going to get? Like translation of AB combined with translation of BA. They'll cancel, right? So what is the result then? Is it a translation? As per the theory, it should be another translation. So is it a translation? Huh? No. Why not? Is multiplication by 1 multiplication? So why can't you translate with a vector of size 0? I do nothing. Okay. So I mean, I can say it's a very bad way of writing it, but vector AA, vector that starts at A and ends at A, it does nothing at all. Okay. Generally, we don't write it that way. We'll write it, we'll denote it as 0. So 0 is the 0 vector. Okay. And you will deal with 0 vectors all the time, even in physics. Like you may have seen what is a velocity vector, right? An object is moving with some velocity. But what if the object is not moving? Does it mean it does not have velocity? It has velocity, just the velocity vector is 0. So zero vector is nothing strange, but the important thing is that this zero vector also belongs to my set. And so what is happening is that this set is starting to look more and more like a group. Okay. So for those of you who have visited groups before, that the objects in that group have inverses. What you just saw is that AB and BA are inverse objects, right? Because if I combine them together, I'm going to get the identity element. So this translation set of translation is a group. So group under and the identity element translation with zero element is the zero vector. So sorry, yes.
Can you explain what is a group?
Okay. I think we may have visited groups before in very basic term, but basically a group is any object which has some basic properties. So like for example, just to illustrate here, for example, is it true that if let x and y, x, y, z are all elements of this set, then basic things like associativity, that I can combine this x, y, z in various orders, right? For example, I can do x composite y composite z or x composite y composite z. So I could apply combine yz first, then apply x or vice versa. But the result is always identical for all x, y, z. So this is what we call associativity. Then similarly, we have a concept of inverse, that for any element in the set, first this is a special element, the zero vector which you already said, right? So if I composite x with the translation of element with zero vector, I'm going to get x again. So in other words, if how to read this, that translation with zero is doing nothing. So if you do nothing and then apply x, it is the same as applying x directly, right? Or if I do it in the reverse way, I first apply x and then do nothing, but I'll get the same output. And finally, the existence of inverse. So inverse meaning that for any element x, there exists a special element which we call x inverse, such that the combined operation of x and x inverse results in nothing. Okay, so so these are three properties, right? This is called associativity. Yeah, sometimes for existence of identity, and this is existence of inverse. Okay, and you're going to find many such objects in mathematics where all these things are true. Okay. In addition, this is also what we call a commutative group. Okay. Because in this list of properties, you'll see that there is one thing which is missing. Does it matter in which order you apply to operations? Suppose you have two elements in this set. Let x and y be two elements of this set. In other words, these are two translations. Then the question is it true that x followed by y is the same as y followed by x or not? That is the question. But you see, this is the flavor of geometric transformation. We started to do geometry, but now suddenly we are doing a lot of algebra. And we never noticed where the switch happened. And after a few lines, we are going to suddenly start doing geometry again. So you are going to keep switching back and forth between this. So this is really a topic which you cannot put any under one bracket. That this is geometry, this is algebra. This is like everything from mathematics is involved in some way or the other. So what do you think? Is it true that does it matter in what order you apply the operation? No. Why? Yes.
Here, take this point, this,
Hmm.
and then this.
Mhm.
This is the parallel.
Yes, correct.
Points gets snapped.
Exactly, correct. So I mean, if you are familiar with the parallelogram diagram which gets formed when you add two vectors, it doesn't matter, right, in what order you apply them. But you see, interesting that to prove something about an algebraic fact, we again have to go back to geometry. That the geometry tells us that if you have, let us say this is the vector x. Okay. I mean, technically it should be given a different name because here when I say x, I'm talking about the operation of translating with a vector x. So this is kind of bit of abuse of notation. Ideally speaking, if this is my vector x, the corresponding object in my set should be denoted by t of x, right? But just let us be a little bit lazy and say that you use the same letter to x to denote the vector as well as the operation of applying that vector. But in your mind, it should be clear that these are two different things. Okay. So the vector x is like this and vector y is like this. Then so here this diagram I'm showing x composite y. No, is it y composite x, right? Because if an object starts from here, first I'm going to apply x and then I'm going to apply y. So going from right to left. So what I've shown here is just the RHS because here x is coming first on the right, then followed by y. But if I wanted to show the diagram of the LHS, that will look something like this, right? It will be simply I'll apply the vector y first and then apply the vector x. And I think just by basic geometry, it follows that I mean, if I call this point C dash, C and C dash have to coincide. Okay. So therefore it is true that, so the answer of this is yes. So the important thing to note is that the answer is not always yes for every group. We are going to see examples of group where the answer is sometimes no. But the translation group is special. And so whenever this is true, that this property is true, we also say it is a commutative. So this is called commutativity. Okay. Or in other words of saying is that you can rearrange the objects in any order you want. Okay, like not just two. If you have 10 elements like x1, x2, x3, and I can apply all of them in any order. I can freely rearrange them and I'll get the same answer. Okay. Just to show an example of a group which is not commutative, rotation, for example. Rotation is a group. So let me, like, for example, so I don't know, those who are online, can you see my phone? So let me rotate this phone. Under some circumstances, it can be commutative. Like for example, suppose I rotate my phone 45 degrees around, okay, we should define some axis of rotation. So let us say, like for everybody's common understanding, let us say that this is my positive axis going to the right. This is my positive y-axis going to the top, and the z-axis is coming out of the screen. Okay, so it is like something like this. and we always do rotation in the anti-clockwise direction. So when I say, like, if the phone is held like this and I say rotate around the z-axis by 45 degrees, I'll be rotating it like this. Okay. Okay. So that is what we mean. So now consider the operation. So first operation is rotation around x-axis of 45 degrees. Okay. So suppose I start my phone like this. So I have to rotate around this axis 45 degrees. So it has to go like this. Okay. And so the question is, if I apply two rotations around x-axis only, will they commute? Like suppose rotation of 45 around x-axis followed by rotation of 90 degrees around the x-axis. So this is my operation 1. This is my operation 2, O1 and O2. So now the question is it true that I can combine O1 and O2 in any order? Will I get the same answer? What do you think? Around the same axis, there is no problem. So, I mean, basically, if I apply 45-degree rotation like this, followed by 90-degree rotation, so I'll get the phone like this. If I do 90-degree rotation first, followed by 45-degree, that is also fine. But now let me take O3, which is rotation around y-axis by 90 degrees. Okay. And now let us say I try to combine O2 and O3. Okay, so O2 is rotation of x 90 degree and O3 is rotation of y 90 degree. And so now try to answer the question. What about O2 combined with O3 and O3 combined with O2? Will it be the same answer or different answer? So let us see. Let us apply O2 combined with O3 first, which means I have to apply O3 first, right? So O3 means rotation of y-axis by 90 degrees. So this is my y-axis. So I rotate by 90 degrees. Then apply O2. O2 is rotation by x by 90. So this is my final position. Okay, so remember this final position. Okay, the phone is pointing in this direction. So this was the answer of this one. Okay. And by the way, now I have forgotten how I had started the phone. So what I can do, I can just keep applying inverses, right? So I again go from left to right. So I have to apply inverse of O2, which is rotation of x through minus 90 degrees. And then I have to apply inverse of O3, which is rotation of y. So this was my original position. So again, so the original O3, O2. Okay, and now what about this? So I have to apply O2 first. So if I apply O2 first around this axis, I will get 90-degree rotation this way. And now if I apply O3, I'm going to get it this way. So if you see in the previous case, the answer was this, but now the answer is this. So rotation is not commutative, but translation is commutative. So, and by the way, this I did in 3D, but in 2D also something similar happened. In most cases, groups are not commutative. Only some special circumstances they are commutative. Okay, anyway, that was just a point to illustrate. But yeah, so this translation group is very interesting. And I mean, I could spend even more time talking about the translation group, but I want to also look at the rotations now. So the first question is, will rotations also form the group of their own? See, the most basic property which allowed us to create a group of translation is that I can combine two translations, right? That composition operation was the important thing. So now the question is, can we compose rotations also? And again, let us talk about 2D rotations only. Let's not go to 3D for now. So I'll erase this part. Just to write the final thing of this. P is question. So the question in its current form is deliberately a little bit vague because I want to see what you think about this first before I give you a lot of ideas. Okay. So maybe let us start with some two rotations, maybe R1 and R2. Okay, so R1 is one rotation and R2 is another rotation. Now for rotation, as we said earlier, that we have to define what is the center of rotation and what is the angle. So the each rotation will have its own center and some angle. So O1 and theta 1, and maybe the second rotation has some center O2 and theta 2. If we start with the simple case that let us say O1 and O2 coincide, okay? So it is the same point of rotation. Okay, so like let this be the same point is O1 and O2 both. Okay. Then what do you think will happen that around this point, let us say the first operation I apply, which is rotation. So the point P is over here. I apply the rotation R1. Okay, so I am basically applying this angle theta 1 to get the point from P to a new position P1, let's say. And then to P1, I apply the other operation of rotation theta 2 again around the same point. Okay, actually my theta 1 and theta 2 look almost identical. Let me take theta 2 to be slightly larger. Okay. So this is theta 2. So here I am applying theta 1 rotation first, then theta 2. Can I think of this as a combined operation of theta 1 plus theta 2? It doesn't have to be two separate operations, right? So now quickly writing the, previously for translation, we wrote a lot of sentences in the middle. But now that we are all familiar with the notation of, composition and all that, how will you quickly write this in one line? That combining the rotation around, and let us call this point O, instead of calling them O1 and O2. So rotation around O of theta 1 and rotation of around O by theta 2 is the same as rotation of theta 1 plus theta 2. So what is the combined, like very nice, crisp way of writing this? And very important reason why this happens to be true is because the distance does not change, right? The distance from O to P, these are all equal line segments. That is why, basically you get one more isosceles triangle over here. And that is why this works out, right? So can I write something like this? That so first I'm going to apply the rotation of theta 1. So I have to write that on the right hand side. And I'll compose it with rotation of theta 2. And so what I'm saying is that the composition of these two operations is the rotation around the same point with the angle theta 1 plus theta 2. So you see the advantage of all the notation we developed so far, that such a powerful idea we can express in one line. That combining two rotations is another rotation, as long as it is, the center of the rotation is the same, O. And here also, do you see that commutativity can be easily established? If I rotate by θ1 then θ2, or θ2 then θ1, does not matter, right? Because the answer is still θ1 plus θ2. So I like just below, if I write rotation of O comma θ1, is the same as rotation. So in the second line, I just reverse the left hand side order, but the RHS is the same. Technically speaking, if you ask me, I should be writing it this way. Just to be, emphasize one point, or very interesting point over here. Let me write it that way. Technically speaking, the first line is θ1 plus θ2, because θ1 is first and θ2 is next, and the second line is θ2 plus θ1. But we know that they are the same thing, right? So the interesting point is this, that the commutativity of rotation follows because of the commutativity of real numbers. The fact that θ1 and θ2 as real numbers can be added in any order is the reason why rotations can be applied in any order. If this were not true, then that would also not be true, right? So you see how one mathematical object borrows from another object, that, because real numbers have this nice property of commutativity, so rotation also gets that nice property. Otherwise, it will not be true. So, I mean, just to put it in a succinct way, the commutative property of real numbers. And why am I saying real numbers? Because I'm assuming that these angles θ1, θ2, they are all real numbers. Implies the commutative property So this is a special case of rotation where rotation is around a fixed point. So we are fixing the point of rotation under which all of this is happening. Okay. But I think this theory is very easy to follow. There's nothing surprising. Like around that point, you can rotate as many times as you want. You're just adding and subtracting that angle. Nothing more is happening. And so again, do you see that there is a potential to form a group over here? Because I can combine two rotations. What will be the identity element? Rotation of angle 0, right? Again, doing nothing. And again, now the question you have to ask is, the translation group also had the element of doing nothing, right? The 0 element translation. And here we have the rotation of angle 0, which is also doing nothing. So are these two kinds of doing nothing separate, or again relabeling of the same doing nothing? So actually, in a way, if I think of transformation as a function from the plane to itself, then both of these are the same operation, right? I can sometimes I'll call it a translation of vector 0. Sometimes I'll call it a rotation of angle 0, but it's the same object that I'm talking about. So actually, that same object belongs to two sets. It also belongs to the set of translations under one name, and it belongs to the set of rotations under a different name. Okay. So this was all about rotation around a fixed point. What about two different points? That is a much more interesting case. Now I'm no longer going to constrain myself that the points of rotation, the centers are the same. So now the picture may be something like this, that point O1 is over here, point O2 is over here. Okay. And so now I have a point P over here. So first operation I rotate by θ1. So point P goes to some new position, let's say P1. And now I have rotate around O2 with a different angle, θ2. And I'll get a new position, P2. So you have a number of questions to answer. That is the combination of these two rotations also rotation? If yes, then under how much angle and from which point?
P2
Mm-hmm.
and draw its perpendicular bisector and take any point like
Mm-hmm.
Lot of rotation.
Okay, yes, okay. So, but the question is, because if I change the position of point P, your perpendicular bisector will change. So, the definition of your equivalent operation should not depend on which point. See, P is just a test point, right? I can move it anywhere in the plane. Okay. So, one important point which will come up over here is that just to revisit again what we did with translations, like let's go back to translation example where we said that the vector AB followed by vector BC is the same as vector AC, right? The important thing is that this property is true for any point in the plane, right? Any point P I can start in the plane. I can apply the vector AB followed by BC and I will get the equivalent answer is. So which point I use to test my operation does not matter. Same thing with the rotation case, like rotation under a fixed point. There like I could choose any point in the plane and that I rotate to theta1 followed by theta2. And I'm guaranteed that the answer I'm going to get is the same as applying theta1 plus theta2 directly. So if I change this test position point to any other position, the whole diagram will change accordingly. So it will always remain consistent. In other words, the definition of your operation should not depend on which point you're using to test. Okay. So your point is valid that I can join P and P2 and on that perpendicular bisector, I can choose any point. But if I change the position of my point P, will that chosen point also change? Does anybody have a guess whether the answer will be yes, no? In your mind, like if you take an object and like if you rotate it by 30 degrees and again by 90 degrees, it appears that the object has rotated by through 120 degrees, right? So maybe the answer is yes.
Excuse me, sir.
Yes.
So according to me, it would be rotation and translation both. Like it would be a composite of both of them.
Okay. Yeah, that can be one possibility because um, so actually what Anushka is mentioning is a important point. Let me talk about this in more detail. See, so far what we have been doing is it is like this. You know, when you're traveling on the road, you can ask the question that if I travel on this road for 100 kilometers, where will I reach? So that is what we have been doing so far. If our starting object is some point P and I apply this transformation, what will be the answer? But now I'm going to ask a different question. I want to reach this position. I want to reach Mumbai. So what should I do? Which road should I take? Starting from Pune, going to Mumbai, which road should I take? That's a different question from if I follow this route, where will I reach? So now what I'm asking is, if I give you the starting object and the ending object, that's what we have here, right? The starting object is P and the ending object is P2. And I have to figure out now which operation I have to apply to go from P to P2. Okay. And to further illustrate the point that the test point should not matter. Like instead of PI, if I choose a different test point, my answer should not change. Let me not use a point. Let me use a line segment. Okay, as my test object. Okay, so I'm going to use a line segment PQ as my test object. So in other words, both P and Q and all the points on that segment are all going to be affected by my operation. So this whole segment PQ will rotate into a new position P1 Q1, and from there again it will get rotated into a new position P2 Q2, maybe something like this. Okay. And so now I have to think that what is that operation from which I can apply to P1 Q1 to directly get to P2 Q2. And what Anushka is saying, can everybody see that a combination of rotation and translation will definitely work? Because what will I do? I'll first translate so that P1 goes and coincides with P2. And then I just have to rotate with the right angle so that Q will go to Q2. So combination of translation and rotation will definitely work. So like if I have to write it in a shorthand, so rotation, like composing to rotation can be written as a composition of maybe, now you have a choice again. You have to do translation first or rotation first. Let us say we first do translation and then rotation. Okay. So I'm in a very shorthand what I'm writing here, that combining two rotations is the same as applying a translation followed by rotation. Okay, like in this diagram, what will that look like? The first translation is this one, right? So this red vector represents the first translation. And then, so when I apply that, this line segment PQ will go somewhere here, right? It will, and the diagram is looking parallel, but that is by accident. But it will be somewhere like this, that green line will get here. And now I just have to rotate so that this point goes here. So this is the second operation. So I think this picture is very clear, but the question is, can we do better? Can we do this in one operation?
So I had
Uh,
a doubt.
yes.
So how would you like get an exact rotation of a line segment around a point not on it? Like this, how would you get an exact one?
So we are asking how will you get an exact, like directly from the starting position to the end one? How do you directly jump there?
No, like so for doing PQ rotated like from O1 to we get P1 Q1. So like
Yes.
you construct it in some way that you get an exact image.
I mean, you are asking like how will you do it with ruler and compass?
Yeah, I mean accurately.
Accurately. Okay. Okay. So I mean, for example, like if this was a real question that you have to take a ruler and compass and actually do the construction, first thing that you will require theta one. Now, I mean, typically in school you are given like 45-degree or some angle, but we are not at liberty to assume it's a good angle. So we are just given a reference angle. So I'm just drawing an angle over here and I'm saying this is my theta one. Okay. So I'm given this theta one angle as a reference in my plane, so I can measure it at whatever I want. And then I'm given this object. So I'm given this point of rotation O1 and I'm given any segment PQ in the plane. And now my task is to rotate this segment around O1 with angle theta 1. And so the question is, how will you do it with ruler and compass? Anybody who can think of a procedure? And let me not take that O1 is very looking like collinear. Let me take that point O1 somewhere here. So what will you do first? What will you do next?
We've been given theta one.
You can.
Have we been given theta one?
You are given theta 1 as an angle there, but we don't know its value. Like if you put a protractor there, that will not work. Like even if protractor says 32 degrees, you don't know if it's 32.000001. So you can only measure it. So how do you measure an angle without protractor? Sir? See, clearly we don't care about measuring. We want to replicate the angle, right? Can we create a copy of the angle without measuring it? So that's what we want, right? We have to copy of that angle at the point O1. Such that, I mean that diagram, that PO1. So you have to form that isosceles triangle, right? So what will you do? thinking. I won't reveal the solution. We have to basically I want to rotate my segment PQ to a new position. So for that, I need this diagram to happen, right? PO1 and P1. And this is an isosceles triangle, right? So how will you construct that isosceles triangle? So do I know everything I need to construct that isosceles triangle? What are the properties I know about that triangle?
So we know the length of the two sides and an angle between them.
Yes. So why can't we construct that triangle?
We
And where
can-
will you construct that triangle? We'll
So-
use that reference angle, right? Yes, Anushka.
Yeah, we can join O1P and
Yes.
then we draw an angle theta1 at O1.
How? That is what I'm asking.
Yeah, so we measure the angle. We keep the
Measure with what?
the needle of a compass at the vertex, and
Okay.
we mark an arc of any length on it.
Okay.
And then from where it cuts the first arm, we keep.
Mhm.
So first of all, without changing it, we keep it on O1 with this
Okay.
measure, and we cut an arc. And then
Okay.
wherever it cuts the first arm, we keep the needle there, and then
Okay.
we adjust it so that it then cut the second arm at the
Okay. So
point.
basically,
it is-
you're going to measure this distance, and
Yeah,
then you're going to copy that distance over
copy.
here,
Yeah,
and then you join this. And that is a copy of your angle.
yeah, and then we cut an arc of O1P to get P1, O1 P1.
Yes. Yeah. I think everybody is fine with this procedure. That you use the reference arc to measure and replicate a triangle. My only question is, Anushka, why are you choosing any length you want? Why don't you choose O1P itself? You see what I mean?
Yes, sir.
So the procedure which I am suggesting is you to join O1P. Let me use O1P as my distance to measure this. So if I use O1P as my distance to make the arc, so these lengths are all going to be of 1. So isn't this the isosceles triangle which I want? Because the angle is theta1 and the two sides are exactly what I want. So I just have to copy this isosceles triangle in my diagram, right? And the way you can do it is again, you measure this length. So basically like SSS test construction, right? From P, you will copy that length over here, and O1P you know anyway. So wherever it joins, so this is my point P1. And I can do the same thing for point Q also. And once I know the two endpoints, I'll get the whole thing. But I'm making a bit of a jump over here. P will go to P1, Q will go to Q1. What is the proof that the all the points in between also go to a segment there? What is the guarantee that in this rotation operation the segment doesn't get twisted or bent in some way? Like I don't know. Maybe this point R, if you apply the same operation, it goes somewhere over here. And so your original line segment now looks something like this. Can that happen? Yeah, you're saying no, but what is the proof? And like those who have studied inversion, you know that there are some crazy transformations that take lines to circles, hyperbola to parabola, and whatnot. So why should a line segment remain a line segment? Just because we are studying congruence transformation. So what is the proof of this? Okay. But anyway, that is it's a very simple thing. Anybody can do it. Simple SSS test, and which is like 10 standard question. So anyway, but we have not answered this question. I just want to point it to you. Okay, but anyway, so now we know how to construct the rotation with ruler and compass. By the way, and same question you can ask for translation also. There it's even easier. That if I give you a vector in the plane at any point, how you apply that operation over there, you'll just complete the parallelogram, right? That will give you. Okay, but coming back to what we are interested in, can there be one rotation which directly takes me from the starting position PQ to the final P2Q2? And even more broadly, now here we are talking about rotation combining to rotation. Even forget the context of that rotation. Let me erase all the diagram in between. And I'm just giving you two segments, the starting segment PQ and the final segment P2Q2. And the only thing I've given is that lengths are equal. Otherwise, it will not happen, obviously. So if I give you two congruent segments in the plane, no matter where they are located, can you create a rotation which will directly go from first segment to the other? Because if we answer this question, then that will automatically solve our first question, right? So let me state. Let me call them PQ and RS. No, I don't call it PQ, RS. P dash Q dash, okay. So PQ and P dash Q dash are congruent segments. Does there exist a rotation?
This one that we translated and then rotated.
Mhm.
So in the rotation, P2 is a variable point, right?
P2 is a variable point, but the angle does not depend, right? See the operation, the first operation, see this R, the red vector. Yes, you have a valid point. What you're saying is actually correct. What is going to happen is that if I move this point P, right, then the position of P2 will change, and that first red vector is also not of the same length. So you're violating the principle that the test point should not change the operation. So like if this translation object itself depends on the choice of the point, yeah, that's a very excellent point. In fact, this is not true at all. So Anushka, I mean, just want to show what was the mistake in what we were doing. What you said is that it can be a combination of rotation and translation. That is true for this diagram where point P is over here. Suppose the point P changes, right? If I choose the different location of a point P somewhere over here, then corresponding to that point P, the P2 will be located somewhere else. And now at this time, the translation we are talking is of different magnitude. So we cannot have that way, that changing the position of the starting point should not change the operation itself. So it appears that it is a combination of translation and rotation, but not for every point in the plane.
So I didn't get it. Like what? I mean, the length of the vector will change, right?
But see, the difficulty is, see, if you go back to the previous example, right? Like where we wrote, just look at this statement, for example. So here I said that rotation of theta 2 and rotation of theta 1 combined gives me rotation of theta 1 plus theta 2. In this, the point itself is not mentioned at all. So even if you change the point, the operations don't change. The operations are constant irrespective of which point you choose. But now what is happening is that the operation itself is a function of the or dependent on the point you choose. So therefore, it is not the same thing. Yes, Raghav.
So I think to find the center of rotation, we can just like consider the intersection of the perpendicular bisectors of corresponding points, like say
Right.
PP prime and QQ prime.
Yes. Okay, so let me draw the diagram. So let us say my segment PQ is located over here and P dash Q dash is located here. Okay, so then what are you suggesting?
Take the perpendicular bisectors of PP prime and QQ prime.
Okay, fine. So yeah, what you're suggesting? So clearly wherever that center of rotation is, it is going to be equidistant from the P and P dash. So it has to lie on the perpendicular bisector. So if I take the perpendicular bisector of P dash and the perpendicular bisector of Q and Q dash, so wherever they meet this point O, so clearly like if we join all the points, okay, so here I'm trying to mark the same length. Right? So do you see we can apply SSS test here because the red line OP and OP dash are equal and OQ and OQ dash are equal, and of course PQ and P dash Q dash are given to be equal. So therefore, so what is going to happen because of SSS test, these two triangles are congruent, and therefore what is going to happen is the angle between them is also equal. So the angle required to go from this red line to this red line will be the same as this one. And whatever is that angle, that is going to be the angle of rotation. So the point of rotation is O and the angle of rotation is this angle in between. But there is a small corner case which is missing.
Yes, sir. What if that two lines are parallel?
So then I think it would be a translation.
So if PQ and P dash Q dash, like if these two perpendicular bisectors don't meet at all, can that happen? Like what if my PQ segment is here and P dash Q dash is here? Oh. So they're congruent, but they're parallel to each other. So now what will happen? Now if I look at the perpendicular bisectors of these, they're never going to meet. But now in the diagram, it is clear that they're going to form a parallelogram. So therefore, we can see that this translation operation can be applied, right? So under this translation, this PQ will go to P dash Q dash. So what it means is the combination of two rotations can sometimes be a translation also. Okay. Well, I don't have a lot of time because I need to leave at 10:30 sharp. But anyway, let me just finish a few things. So now we know that if there are two non-parallel segments, that one rotation can finish the job. So going back to the previous question where we are trying to combine two rotations, right? So combination of O1 and O2 together. See, now the difficulty we need to solve is fine. So we now understand that we can find out the point around which PQ will directly go to P2Q2. Okay. Suppose that point is O somewhere over here. Okay, maybe. And how much will be that angle of rotation? You see, it will be theta1 plus theta2 because of the look at the line segment itself, like it is rotating through angle theta1 and then through theta2. So the total angle through which it is rotated from the starting is theta1 plus theta2, right? So no matter which is the center of rotation, that angle was always going to be theta1 plus theta2. Okay. So let us say we get that the point O is there, and around that, if I rotate it with theta1 plus theta2, P goes to P2. But now I need to establish that there was nothing special about the point P and Q. If I change the test point, if my point O also changes, then it is all waste. So what should ideally happen is that even if I change this point PQ to some other position, O should not change. Only then can I say that, then like hopefully the conclusion I would like to write is that this combination, right, the rotation of O1 theta1 combined with the rotation of O2 theta2 is the same as the rotation of around this point O with angle theta1 plus theta2. This is what I would like to write. But the important property being that the point P is not there in this equation anywhere. And that will only happen if changing the point P does not change the point O. Okay. And so that is something for you to discover and establish going home. That is it really the case that the point O does not change? Okay. But I mean to conclude on the question of whether rotations can be composed. So the answer is rotation plus rotation. So basically rotation and rotation combined is either another rotation or a translation. And that purely depends on the angle of rotation. So what happens is if you rotate by angle plus theta and by minus theta, okay, then you see that basically you have made the object parallel to itself. Like for example, look at this diagram. So point O1 is over here. I rotate an object by 90 degrees, okay, just to keep things simple. So this original segment PQ is over here. I rotate by 90 degrees to get a segment P1, Q1. And now under a different point, I don't have to choose the same point. On a different point O2, I rotate by 90 degrees, but in the opposite direction. So first was anti-clockwise, now I'll rotate clockwise. So what will happen? This P1 will go somewhere over here. So you'll get a segment like this, right? And so this original PQ and P2Q2 are parallel. And so now this is the case where, as what we saw earlier, that will require a translation to go from here to here. So you see the translation happens where these two angles of rotation, like if I call them theta 1 and theta 2. So now you see the condition under which it is going to be rotation and the condition under which is going to be translation. So it is going to be a translation if what? If theta 1 plus theta 2 is a multiple of 360 degrees. Right? So like plus 90 minus 90 will work, or some other case like 90 and 270 degrees. Actually 270 is the same as minus 90. If you think about it, it's just in the opposite direction, right? So it is a translation if theta 1 plus theta is some multiple, else it is always going to be a rotation. So almost always it is a rotation, only some special cases it is going to be a translation. Okay. But see, so far we have not done any questions like what can we apply this in any actual problems, or is it just for theoretical knowledge? So let me share one problem, and we won't be able to discuss the solution today, but you can think about it and we will discuss next time. Okay, it's a very interesting construction problem. Okay, the problem is something like this. So you take a triangle, okay? Everybody knows how to draw a triangle. And on the triangle, on the three sides, I will draw an equilateral triangle. Oh no, let me choose isosceles right angle triangle, not equilateral triangle. Okay. Don't ask why. So I'm going to create this 45, 45, 90 triangle on all the three sides. Okay, so triangle ABC is any triangle, and these are 45, 45, 90 triangles on the three sides. Okay, let me call these outer vertices as maybe P, Q, and R. So if I give you triangle ABC, obviously you can construct the points PQR. Anybody can do that. But what I'm going to ask is the reverse. I'm going to erase the whole diagram and only keep the points PQR. So now the diagram is like this. P is over here, Q is over here, R is over here. We don't know where ABC is. And now your job is to construct triangle ABC using ruler and compass. Such that for that triangle, if you complete this diagram, PQR will go in those positions. Okay, did you understand the question? Ruler and compass to construct. By the way, anybody already knows this question or how to solve it? Online, anybody who knows this question already? I'll give
There is a question workshop where it was equilateral.
equilateral triangle on all three sides. Okay, but yeah, so yeah, this is a isosceles right angle triangle. But what I'm going to share next time will show that it doesn't matter which triangle you take. You can pick your own favorite triangle. and the question can still be solved. Doesn't have to be a triangle also. Can be a favorite polygon. Just to share why this is so powerful. We are going to solve this question next time. That we'll have a triangle. On that triangle, I've created isosceles right angle triangle on all three sides. And then if I gave you those outer points to begin with, can you construct a triangle inside? That is the question. But I could have easily asked you this question. What is the year 2023, right? Consider 2023 sided polygon. Okay, so P1, P2, P3, P4, P 2023. Okay, and now on this 2023 sided polygon, I'm going to do the same thing. Isosceles right angle triangle everywhere. Okay, triangle, triangle, triangle. Okay. And then what I'll do, I'll only keep those outer vertices and I'll delete everything in between. So you have this like 2023 outer vertices, and now you have to construct the polygon inside. Once you solve this question, you'll also solve this question. Okay. So this is very, like today's lecture was mostly about developing the theory of transformation. Next lecture, we'll see how to apply this in very powerful ways. Okay. So anyway, but I think you have 1 week to think about. Yes, Raghav, you already know this question by any chance?
No, but I think I have an answer solution.
Okay. So then wait, let everybody try. Maybe you can send it on WhatsApp to me.
Okay, sir.
But anyway, I have to stop for today. So yeah, see you next time. Okay, thank you. Bye.
Bye, sir. Thank you, sir.
Thank you, sir.